Now, the motion of a conductor through a fixed magnetic field also causes induction. This kind of induction is called motional EMF. So we're going to consider this circuit and this image here. We've got two conducting rods on top. They're connected on this end by a resistor, and on this end there's a metal bar running across. So all of these pieces create a closed circuit. And this circuit lives inside a magnetic field shown here. Okay, so as this vertical rod here moves to the right, the area that is enclosed by this circuit increases. So our magnetic flux is equal to the magnetic field times area. So if the magnetic field stays the same, but the area increases, we increase our magnetic flux. So if we look at Faraday's law, ignore the sign on it for now, and consider one loop, then the EMF we induce is equal to the changing magnetic flux over time. We said magnetic field was stationary or constant. The area is changing, so that's a changing area over a changing time. Okay. Now the area we can write as the length of this rod times some distance that it's moving through horizontally. Okay. So we're going to write that as BL delta X over delta T, because L is stationary, X is changing. The horizontal distance there is changing. And remember that a change in position over a change in time, that's a velocity or speed. So we can write this motional EMF as the magnetic field times the length of some conductor times the speed at which that conductor moves. Now this is a special case where the magnetic field and the magnetic field and this length of my bar here and the speed are all perpendicular to each other. So in this situation, Lenz's law will give us the direction of the induced magnetic field and current, and our right-hand rules, we're going to use both of them, give us the direction of the current and the magnetic force on the bar, which we're going to practice with the problem here. So we have a sliding bar, this bar here, with a length of 0.5 meters, and it moves at 2 meters per second in a magnetic field. Here, this magnetic field is into the board of a magnitude of 0.25 Tesla. We're going to find the, let's just say, induced EMF and current in the moving rod, calculate the magnitude and direction of the magnetic force on this bar, and then calculate the magnitude and direction of the force we have to apply to move that bar at constant speed of 2 meters per second. So what we have here, we've got two conducting bars on top and bottom. They're connected on one side by a wire that has a resistor, and then they're connected on this side by a conductor that can slide back and forth, okay? But in this case, we're taking this metal conductor and we're sliding it to the right, okay? So it has some velocity vector to the right. So we're moving our conductor through a magnetic field, and that magnetic field here is constant and is pointing into the board, okay? And as my this bar here gets slid over, this distance x is going to increase over time, okay? And then this length right here from top to bottom of these top and bottom conductor, we're calling that length L, okay? So we have this sliding bar, the length from top to bottom here is 0.5 meters, and we're moving it at a speed of 2 meters per second, and the magnetic field is into the board with a magnitude of 0.25 Tesla. Okay, and so the first part, we want to find the current and the voltage induced as we move our rod to the right. So we're looking for I and the EMF induced. Okay, what are those? Well, let's just think about the magnitude of the EMF that we induce. With Faraday's law, our magnitude of the EMF is going to be the number of loops that we have. We only have one loop here, times the change in magnetic flux over the change in time. Okay, so remember that the magnetic flux is BA cosine theta, the change in that. Our magnetic field here is constant in magnitude. So B is constant. The thing that's going to be changing is our area. So delta A is changing, and then cosine theta. Theta is the angle between our magnetic field vector and the vector perpendicular to our area here, but in this case, cosine of that angle is going to be 1. Okay. And then we divide that by delta T. Okay. Now, my change in area, well, we can also write this. The magnetic field, okay, so my area is length times width of this area of the circuit that I have here. As I move my bar to the right, I'm actually increasing the area of my circuit. And the area, if we think about it as being the length times the width, but this width is growing. And it's growing at some rate that I'm going to call delta x, okay, the change in x. And we divide that by a change in time, okay? Remember that a change in position over a change in time, that is a velocity. So here we've arrived at our equation for motional EMF, that the EMF we can induce is equal to the magnetic field times the length of my conductor times the speed at which I'm moving it through this magnetic field. So that's the equation for the motional EMF, which we've just derived. So now I can plug in my magnetic field strength, 0.25 Tesla, multiply it by this length here, 0.5 meters, and then also multiply it by my speed at which I'm moving this bar to the right. So that's 2 meters per second, okay? And so then I have 0.25 times 0.5 times 2, so the induced EMF is 0.25 volts here, okay? Now, for the current running in my circuit, we can use Ohm's law, V is equal to IR, solve it for I. Our induced current is going to be equal to our induced EMF divided by the resistance of the circuit. So we do have a little resistor here, which has a resistance of, oh, I didn't tell you that, 0.5 ohms. So our current is going to be 0.25 volts divided by 0.5 ohms, and that is equal to 0.5 amperes, okay? So we have an induced EMF and an induced current in my loop, okay? Let's think about the direction of the current in this circuit. So we've already calculated the magnitude of the current and the magnitude of the EMF induced. So as we're, this current that's induced, the direction of that current is going to be opposing the change in magnetic flux. Okay. So in this problem, our magnetic flux is increasing. So our magnetic field that our circuit is embedded within is constant. But as we move our conductor to the right, we're increasing the area. That means that we are increasing the magnetic flux. And if we have an increasing magnetic flux, then the induced magnetic field will want to oppose the magnetic field that's already present in our problem. Okay, so since the magnetic field is already into the board in which our circuit is embedded, that means that our induced magnetic field is going to be out of the board. Okay, so B induced will be pointing out of the board, all right? And so then if we use our right-hand rule to figure out the direction of the current, if our induced magnetic field is out of the board, I'll use my second right-hand rule here. And remember that second right-hand rule, my thumb points in the direction of current and my fingers curl around in the direction of the magnetic field. So inside my loop here, I want my magnetic field, which was induced, to be pointing out of the board toward you, okay? So if I do that then, if my fingers are pointing out of the board, they're curling around and out of the board on the inside of this loop here, then my thumb has to be pointing in this direction to the right on the bottom here, okay? Now if I come up here to my rod, conducting rod, and use again my second right hand rule, inside the magnetic field needs to be pointing out of the board, so curling around, pointing out toward you. That means that my current with my thumb direction has to be pointing up, okay? And so that means that the current in my circuit that I'm able to induce is a counterclockwise current, okay? Counterclockwise, opposite the direction of the clock, so it's going around in this direction. So that's important for us because we're going to use that in order to help us figure out the magnitude and direction of the magnetic force that's now acting on this conducting rod that I'm sliding through here. Okay. So, draw that in a little bit better. There's my conducting rod. Okay, so the magnetic field, or sorry, the magnetic force that this conducting rod feels as it's got some current running through it and it's moving through a magnetic field, or it's subjected to a magnetic field, that magnetic force is equal to I-L-B sine theta. Okay. Theta is the angle between our current and our magnetic field. In that case, sine 90 is going to be 1. Okay. So we've got our current induced. We found that magnitude, 0.5 amperes. We've got the length of our conducting rod here, which was 0.5 meters. And we've got the strength of the magnetic field in which this permanent magnetic field in which my bar is moving, that's 0.25 Tesla. Okay, so the magnitude of this magnetic force that this bar feels is going to be 6.25 times 10 to the minus 2 newtons. Okay, so what is its direction? Now, if we use our first right-hand rule, it will help us figure that out. So I've got my current running upward, okay? That means that the velocity of the electrons in the current are going to be pointing in the opposite direction. So my thumb will be pointing down here, okay? Because that's the direction of my speed of my electrons. And then my fingers are pointing into the board because that's the direction of this magnetic field through which this bar is moving. And I'm talking about electrons, so that means that the backside of my hand tells me the direction of the magnetic force on an electron. My palm would tell me the direction of the magnetic force on a positive particle. So on a negative particle, my electrons, which are the charge carrier, is going to be pointing in this direction here to the left. So my magnetic force is going to be pointing in the opposite direction of the motion of our rod here. Okay, so the magnitude of the magnetic force, 6.25 times 10 to the minus 2 newtons, in the opposite direction of its motion. So now let's figure out what is the magnitude of the applied force I have to give this, this conductor as I slide it across in order for this speed to remain constant. If I have a constant speed here, okay, then that means that the magnetic force is going to be equal to, in magnitude, but opposite of direction of the force that I've applied, okay? So that's one way you could think about it. If we think about Newton's second law, the sum of my forces equals ma. If the speed is constant, then the acceleration is 0. So that means that my magnitude of my magnetic force has to equal the magnitude of the applied force in order to keep this thing moving along in equilibrium, okay? But there's another way we could figure out the magnitude of the applied force. And we could do that by thinking about work. So the work that I'm applying to move this bar is equal to the force that I apply through some distance, okay? And also work is equal to power times time. So I solved this for the applied force. The applied force is equal to power delta t over the distance that I move it, okay? But remember that distance is equal to velocity times time. So this is also equal to power times the change in time over v delta t. So my change in times cancel. So we've got that the applied force is equal to the power divided by its speed. Okay. And our power is also, guess what? Current times the induced EMF. So the induced current times the induced EMF divided by, maybe we'll make this top one a big V, or our applied EMF, or induced EMF, and on the bottom we've got the speed here. So we could also find the applied force by taking our induced current, 0.5 amperes, times our induced EMF, 0.25 volts, and divide that by the speed at which I'm moving my rod, 2 meters per second. And if I do that, then I also get back that my applied force here would be 6.25 times 10 to the minus 2 newtons. Equal in magnitude, but opposite in direction.